Hi, class. So we're going to start with a quick overview of organic chemistry as a whole, and then we're going to move into electrons. And part of the reason we start this class with electrons is they're so important in bonding. And so as we kind of move forward and build molecules, electrons will be the key component that builds those molecules out. So that's why we kind of start with what chemistry is, and specifically organic chemistry, and then move on to electrons. So let's just start there. So you probably all had Gen Chem, and you kind of did a brief overview of everything in chemistry. So what we're going to study here is primarily the compounds that have carbon in them. And it seems like we're simplifying this down to one carbon atom or one set of atoms, including carbon. And the problem with that is that you could still make so many different molecules, right? And that's why it needs its own class. Right? So even though it looks like we're simplifying the problem, there's actually millions and millions of molecules we can make. We can make a bunch of different molecules, right? So single bonds, doubles, triples, and those are all made with electrons, right? So we talked about that electrons are going to be really important in bonding, and this is what we're going to come back to is how do we make these bonds? Right? The last one, it's about an intermediate electronegativity. So if you remember in Gen Chem, and so I can do this really quickly, if we think about electronegativity, if you think about your periodic table, as you get towards fluorine, we become more electronegative. And so if we really zoom in on kind of this portion of the periodic table, it goes carbon, nitrogen, oxygen, fluorine. And even though hydrogen, if you look at the periodic table on the left, tends to be up at the top, for electronegativity, it tends to be closer to carbon. All right, so it's a little less electronegative than carbon. And so if we were looking at the periodic table, it really should sit next to carbon in terms of electronegativity. All right, and so that's something to keep in mind as we're kind of going forward. All right. As we're looking at this, most of the molecules we're going to look at are going to be based with carbon. So we just said that, hydrogen, and then we'll start to mix in a few other atoms, particularly oxygen and nitrogen will show up a lot. Right? And we'll see some other metals and a few others here and there, but those four are really the ones that we'll study a lot in this class. One last thing, and this is more big picture of why you take organic chemistry. Organic chemistry shows up in a ton of health, right? Or medicine, biochemistry, biology. So most of the molecules in our body are organic molecules. So all the proteins, peptides are all made of organic molecules. Lipids, organic molecules. Most of the medicine we take, penicillin, aspirin, even caffeine, if you're enjoying a coffee while you're listening to this video, caffeine is an organic molecule. So it shows up in so many different aspects of our everyday life. That's why we kind of spend so much time on just one genre of chemistry. All right, so let's jump right into electrons. So I know you saw this in Gen Chem, but I felt like it was worth just kind of reviewing. All right, so remember, we're going to think about electrons that in the middle, if this is our nucleus, remember our nucleus is made up of neutrons and protons. Now, outside of that is our electrons, and they're going to be floating around the outside. And I'll usually use E with a negative charge for electrons. Right. The way people used to think about this is more like a sun and the planets orbiting around it. We've kind of realized that that's not really exactly how it works because it's more of an electron cloud. But in terms of these shells, it actually works pretty well to visualize it. So the first thing that we're going to look at is the S shell. And the S shell is just a nice sphere, right? So it makes a nice circle. The p orbital is an hourglass. And as we go forward, there's other shells such as the D, and you probably talked a little bit about this in Gen Chem. The nice thing about organic chemistry is we typically only deal with the outer shell, which is 8 electrons. And so we'll only use the S and the P. Now, what I want to bring your attention to is kind of the bottom here. And so what you should think about is that each one of these shells can hold 2 electrons. So now in row 1, the total amount of electrons we can have is 2 electrons. Right? And remember, the E with the negative charge just means electrons. All right, so this is going to be our shorthand for electrons. Now, this would be that first shell. And now as we move our way out, right, there's a second shell. It's still going to have an S, right? So that'll have 2 electrons. Now, each one of these p orbitals, and there's actually 3 of them, right? Px, py, and pz. Each one of these can also have 2 electrons. So I'm just going to put a 2 electrons for each of these. So if we're thinking about this, in the second level, right? So in the second shell, we can have a total of 8 electrons. Carbon sits in the second shell, and this is why we're going to spend so much time with this 8 electron rule, right? So we're typically going to try to fill up the second shell, right? And we're going to talk about different ways we can do that here in a second. But here in a minute, you're going to hear me constantly refer to the octet rule. And where the octet rule comes from is filling up this shell with 8 electrons. Right? And so the orbitals they're always going to be in is the 2s, 2px, 2py, and 2pz. Now, I highlighted this other one, this d orbital. So at the very end, we'll talk about some of them having expanded octets or metals that can have different electron rules. A lot of that variation comes from having these d orbitals, and they give a lot of metals and some of the elements lower on the periodic table a lot more flexibility on the terms of what electron rules they have to follow. But mainly for our class, we're going to follow this octet rule, and it's going to be to fill up these 8 electrons, right? So that's where the octet rule comes from. All right, so let's think about this. So I think when you had Gen Chem, right, you had to do an electron configuration. And so let's just do it for carbon, and we'll kind of do it along this kind of cheat sheet of the different principles of our electron configuration. So carbon, if we look at our periodic table, right, has an atomic number of 6. And if you remember, if the atom's neutral, the atomic number equals the number of protons. So we'd have 6 protons. And remember, if it's neutral, it'll have 6 electrons. So if we think back about what the orbitals look like, this would be our energy. So we have the 1s. And then what we're going to have is the 2s. And then our 3 p's. So px, py, and pz. All right, so let's just start going up through each one of these principles and fill up these electrons. So we know we have 6 electrons, and we're going to try to figure out where they go in this energy diagram. So the very first statement says we're going to fill these from increasing energy. Right? So we want to start with the lowest energy and go to the highest. Okay? So the lowest energy just means start at the bottom and go up. All right, so we know that we have to put our electrons in the bottom. Okay? So we're going to put them here. And these arrows are just going to signify my electrons. Okay? So this tells me I have 1 electron, a second one. And if you remember from the previous slide, we'll only ever put 2 electrons in each orbital. So that's how we knew that we could only put 2. All right, so we want to fill up the lowest level before we go up. All right. So the second one says there can't be any more than 2 electrons in any orbital. Yep, so what we just said, right? That it can only ever have 2 electrons. And so that's why there's only 2. Right? So just a fancy way of saying they can only hold 2. All right, so not too bad. The last thing this one says is if there's 2 electrons, their spins must be paired. The way we highlight that is we put these arrows in opposite directions. All right. So just like magnets, right? So you won't put the same charge of a magnet against each other because they'll repel. Instead, you put the opposite charges and they attract. Same thing here. So we're going to have one spinning one direction and one spinning the opposite. And that's how we show that they're paired. All right, so let's keep going. So we have 6 total electrons. We've used 2, so we still have 4 more. So we can put 2 more in this one. Now we still have 2 left. And we want to decide what we're going to do. So we can either spread them out, or we could pair up the first one and just kind of leave the other ones empty. So this last rule tells us that if the orbitals are of an equal energy, so let me highlight this because this is an important thing. If the orbitals are of an equal energy, then what we want to do is add 1 to each of the orbitals before any of them get a second electron. Okay. So all this is telling me is that if there's several at the exact same level, we're going to put 1 in each of the orbitals before we start pairing them up. So this would be our electron configuration for carbon. And so let's just go back and kind of do these 3 rules in row. So we start at the very beginning. We're going to fill up the very bottom orbital. Remember, each orbital can only hold 2 electrons. Remember, so they can only hold 2 electrons. And then we're always going to pair them up. So meaning they're going to spin in the opposite direction. Once one of them's filled, we move to the next highest. We fill that one up, and then we move up to the next highest. If there's more orbitals than we can fill up, then we put 1 in each of the electron orbitals, and then we would go back and pair them up. So if we had a third, and let me put it in a different color just so you know that this isn't part of carbon, but if we had more, then we would add 1 here, and then follow up, and we would just keep going until we get paired up. All right. And so we put 1 in each of them, and then once each orbital has an electron, we go back and we start pairing them up. Here's a little bit better drawing than me. So this is the same thing we just did. So the one on the left is carbon. And so what we've done here is exactly what we did. We said we'll always start at the bottom. And this represents our 1s shell. And we put our 2 electrons. As you can see, there's a big energy gap between the 1s and the 2s. But once this one's filled, we move up. We're going to fill the 2s first. Once that one's filled, then we start putting 1 in each of the p orbitals till they're completely filled. Right? We ran out of electrons, so we just stop wherever we're at. And this is the same for any atom. Right? So chlorine has 17 electrons. And so we would just start at the bottom and do the exact same process and keep working up. This one has an extra shell, right? Because it's 1 row lower on the periodic table. So then we move into the 3s and 3p. All right, so what I want you to do now is we're going to try this for nitrogen. And it has an atomic number of 7. All right, so pause the video and draw a chart just like the one we have here. So you're going to redraw this. It'll look just like this energy diagram. And I want you to fill it up. So first figure out how many electrons it has, and then what the chart would look like. All right, so if you want to pause the video and give that a try, and then we'll do it together. All right, so hopefully that wasn't too bad. So we'll have our energy here on the side, and I'll just use E for energy. We'll start at the bottom, and it'll be our 1s. Then we'll have our 2s. There's only 1 orbital. Our 2p. And then remember, if it's a neutral atom, so nitrogen doesn't have a charge, it's going to have 7 protons and 7 electrons. So I'm running out of space. I'll just use my shorthand. So we have 7 electrons we've got to fill up. So let's just start from the bottom and work our way up. So the bottom one gets 2. And remember, they're always going to spin in opposite directions. Right? So one's going up, one's going down. We move up to the next level. 1 goes up, 1 goes down. Now we've used 4 of them. We have 3 left. So that means we're going to put 1 in each of these. And that would be our electron configuration. Right? If we had another electron, remember that's when we go back and start pairing them up. Very good, class. Make sure you can do this. I'll definitely ask you something about electron configurations on both your Chem 101 homework or on an exam. The other thing we can do is write out our electrons. So one of the things I'll ask you to do is draw the electron configuration. We won't do that for every atom because it would take you forever. So one of the shorthands we do is we just write the shell and then the orbital that it's in. All right. So for hydrogen, it has 1 electron. So it's 1s1, meaning it's in the first shell. It's in the s orbital. And then the superscript explicitly tells you how many electrons are in that orbital. All right, so remember, the most you can ever have is 2. But if you don't have 2, you have to show how many it has. So that's why hydrogen only has 1. All right, same thing for lithium. Right? It goes 2s2. And what we do to cheat a little bit is so that we don't have to write out in a giant electron configuration, right? Lithium could actually be 1s2, 2s1. But what we can do is replace the 1s with helium. And essentially what we're going to say is that up until that atom, they're exactly the same. Right, so we'll come back and work through more of these in the second period, but let's look at the third period. If you're looking over at sodium, see how this one has neon in parentheses? That means the electron configuration up until that point is exactly the same as neon. And so if we wanted, what that bracket tells me is that sodium is 1s2, 2s2, 2p6, and then the 3s1 is the only thing that's different. All right, so everything in this column would have that electron configuration in red. Okay. Same thing over here on the left. This purple one, the 1s2, that means everything in this column starts with 1s2 and the only thing that's different. And so what we're actually writing out are the valence electrons. So this is important. Put a star by this. When we say the term valence electrons, it's the outermost shell. All right, so the valence electrons are the groups in the outermost shell. And the reason we care about those are they're the ones that tend to do the most chemistry, right? So they're the ones that tend to do the reactions, that do the bonding. So that's why we care the most about it. All right, and we're going to come back to that here in a second. One more thing I want to point out. If we're looking at the second period and we keep going down this column, it says 1s2, then we put a second electron and it's 2s2. 2s2, 2p, right? If we think back at our previous one, we're starting to fill up that p orbital and we're going to keep adding them in 1, 2, 3. Now, you're probably saying, well, Jimmy, you just said that you can only put 2 electrons in each orbital. Why is there 3? When we do this notation, we don't separate the difference between the p that has an x or a y or a z. We just combine all the p orbitals. All right. So even though there's 3 different ones, right? There's px, py, pz. We combine them all. And so since there's 3 of them and each of them can hold 2, we can actually get up to a total of 6. And when we're doing this configuration, we actually don't really care if it's in X, Y, or Z. They're actually very similar, so it doesn't really matter. It's more of a nomenclature for us. And so we can get up to 6 electrons. So if we scroll back up, so let's just go back a slide. If we were going to do this for nitrogen, we're just literally going to write it the way it is. Right? So we say the 1s, so let's put that first. And we count the number of electrons. There's 2, so that's why the 2 goes on top. Now we go to the next one, it's 2s. We count the number of electrons. There's 2, so we put 2 on top. All right, we can do the last one. All right, so it's P. We count, and it's 2P. 1, 2, 3. So it's 3. So for nitrogen, its electron configuration would be 1s2, 2s2, 2p3. Okay. And so for practice, you can do the same thing with both of these. Right? And so I'd go ahead and give these a try, and then you can check your answer on the chart below. The next thing we're going to talk about, and we're going to come back to these kind of to get and put it all together. But one of the things that we're going to use to kind of predict what a molecule is going to look like is molecules always want the lowest energy possible. All right. And so when we're going to look at small molecules, like what we're going to do in this class, or when you move on to like a biochemistry or some of your biology courses and you look at a giant like proteins and enzymes, they still all have that same principle that they're trying to get to the lowest energy. Right? So that's why we spend a little bit of time talking about generally what energy is, but then specifically how that relates to the structure of a molecule. Right? So energy in a more global sense is the ability to do work. Right? And that kind of makes sense, right? Even if we think about it from our perspective, the more energy we have, the more likely we are to go out and do something, run errands, study, right? And so if we have energy, we're able to do things, right? Potential energy is a stored energy, right? And I think probably you heard this somewhere in high school. If you take a ball and you hold it up really high, it has a ton of potential energy so that when you drop it, it's going to have more force when it comes down, right? So we're going to talk about different ways we can store that potential energy, right? And then how do we release it, or how do molecules release it? Now, where this is going to relate to our class kind of in the immediate future as we kind of work towards this idea is unstable structures tend to have really high energy that's waiting to be released, right? So they're unstable, so they typically release energy and go to a more stable conformation. So they tend to be in this really high energy state. And then whenever something changes, it changes because it drops down to a lower energy level. And that amount of change is the amount of energy released. Right? And so that's where this idea of molecules will always want to be the lowest energy conformation, and they give off that energy that gets them from the high energy state to the low energy state. Right? On a very practical version, one place people see this is when do we burn energy or get energy from? Burning gasoline, right? So we harvest that energy. One thing that's kind of neat about organic, especially if you kind of go on to take biochemistry, we're going to learn about oxidation and how we change molecules. Our body does the same thing. And so one of the things we do is we drive our cars, we burn gas to make our car drive and move and get places. Well, when we eat food, we're actually doing combustion on those molecules as well. And it's just a little bit more elegantly, but eventually they turn into CO2 and we get energy out of them. Now, if we kind of tie this idea of energy, and we've already seen it, right? When we're doing the energy diagram, we had our energy diagram where we put energy on one side. And let's do this again for carbon. We had our 1s, 2s, and then our 2p with our 3 orbitals. And we could fill these in. And so we said this had 6 electrons. So we'll put 2, 2, and 2 more. All right, so what we want to look at is electrons that are held closer to the nucleus. The nucleus would be down in here. So the 1s is the closest one to the nucleus, right? And so they're held the tightest. As we move further away, they're held a little less tightly, and they're easier to remove, right? So the electrons on the shell farthest away from the nucleus is going to be easier to remove. Right? And so typically it's those outside electrons. And does anyone remember, we just talked about this on that previous slide, not the energy one, but the one with the electron configurations. What are those outermost shell called? It's the valence electrons. And so it's those valence electrons that we can pull off, right? And so when we talk about ionization energy, it's the energy needed to remove that most loosely held electron, right? So that first electron that pops off. And the reason we care about that is typically if you see an atom with a charge, so a plus or a negative, it means a plus means you lost an electron. A negative means you gain an electron. So we're going to look at those different energies. So in order to get a plus charge, it means you lost an electron. All right. So for example, if we have something like sodium, you have a sodium metal, it has one valence electron. If we lose that electron, so that arrow is telling me that we're losing that electron, it just becomes sodium and we put a plus charge. So every time we lose an electron, we get a plus charge. All right. And so what I just gave you an example of is Lewis dot structures. All right. So Lewis dot structures tell us what an atom looks like. All right. So what we care about are the outermost shells. Right. So this is our valence electrons. So we just talked about our valence electrons, and they're in our valence shell. Right. So the valence shell is just the outermost occupied electron shell. Right. And the valence electrons are specifically those electrons in that valence shell. All right. So the way we're going to do this is we're going to do our Lewis dot structure, and we're going to draw the structure, okay, with the atomic symbol in the middle, and then we're going to use dots to represent the electrons. Okay, so if we did this for carbon, our atomic symbol for carbon is C, so let's put carbon in the middle. Okay. Now, over here on the left, I'm going to write out our electron configuration. So carbon is 1s2, 2s2, 2p2. All right, so this is my electron configuration for carbon. Now, that outermost shell just means the electrons in the outermost. So in this case, it's everything with a 2. Right? It doesn't have to be a 2, it's just the highest number. Okay. So for carbon, it's the second shell. So all of these electrons are in my valence shell. And the total number of valence electrons I have is 2 plus 2. So for carbon, I'm going to have 4 valence electrons. Now, the way you're going to draw this is you almost want to envision that there's a box around carbon. Right? So if you're assuming there's a box around carbon, the way we can do this is we're going to put, move this over, we're going to put 1 electron on each side. And that would be our Lewis dot structure. All right, let's try the same thing for oxygen. All right, so oxygen has an atomic number of 8. All right, so go ahead and pause the video, and you're going to do 2 things. Draw the electron configuration, and then draw the Lewis dot structure. All right, go ahead and give it a try, and then we'll do it together. All right, so your electron configuration, remember we start at the bottom. So it's going to be 1s2, 2s, and then 2p. And if you remember, as long as the atom's neutral, if it has an atomic number of 8, it's going to be 8 protons and 8 electrons. So that means we've already got 2, 4, and so we need 4 more. And so we put our 4 electrons. Now, if we highlight these are my valence electrons. So I have 6 total. So remember, the way we're going to start this is we'll put the atomic symbol in the middle. So we put our oxygen. And now we want to start putting 1 dot on each of the faces, right? We're going to pretend that there's a square box around it, right? That there was a box. And we're going to start by putting 1 dot on either side. So we get 1, 2, 3, 4. We still need 2 more electrons. And so now, just like we did with the p orbital, we go back and start pairing them up. So we get 1. And it really doesn't matter which groups you paired up, the top or the side, as long as there's some paired up, that's all that really matters. Something that we're going to use as we kind of go forward on these Lewis dot structures is electronegativity. Remember, always goes towards the fluorine, right? So fluorine is the most electronegative atom. Okay. And what electronegativity means is just how much do you want to steal electrons, right? So we're going to pull electron density towards us. Okay. And so if we're sharing electrons, they're going to go towards the fluorine. And if you're trying to decide if an atom's going to give up an electron or steal an electron, the more electronegative you are, means the more likely you are to steal them, right? And it's going to be harder and harder to get rid of them, right? They're going to really want to hold on to it. It uses the Planck scale. Essentially, it makes fluorine equal to 4. And then the smaller the number gets, the less electronegative. All right, so we think the least electronegative atoms are down here at the bottom left. The most electronegative atoms are up here on the right. All right, so the top right. You don't need to memorize these numbers, but if you just want to be able to specifically see them, we just said that fluorine is the most electronegative with 4. And generally, the closer you are to fluorine, the more electronegative you are. Okay? And I think I talked a little bit at the very beginning that even though hydrogen is here on the left column, in terms of electronegativity, it actually belongs right next to carbon. Right, so it'll sit right there. And generally, the rule of thumb is if you're up close to fluorine in these nonmetals, you're going to be very electronegative. If you're down over here on the left part of the metals, you're going to have a very, very low electronegativity value. And remember, electronegativity just means how much you want electrons, right? So fluorine is probably always going to have a negative charge if it has a choice to donate an electron or grab an electron. It's going to grab one, so it's going to pull the electrons towards it. Right. And so let's actually specifically look at this. So I know there's a lot going on here, but essentially what we're going to think of is there's a couple ways to help electrons fill that outer shell, right? So we talked about having those 8 electrons and that was going to kind of be this octet rule that I had hinted at. So what we actually want to see is how do we get those 8 electrons? So one of the things we can do is look at 2 atoms. So if you're looking at sodium, it has a 1 electron here that's a little hard to see. And then fluorine has 7. And remember, these are our Lewis dot structures. So we're only showing the valence shells. So we only care about the valence electrons. Sodium has 1 valence electron. Fluorine has 7. If the electronegativity difference between the 2 atoms is 2 or greater, so higher than 1.9, we're going to transfer the electrons instead of sharing. All right, so that 1 valence electron is going to jump over. If you have a curved arrow, what that's going to tell you is the movement of electrons. And just a little bit of notes, if it's the barbed arrow, it's just 1 electron. If it's a double-headed arrow, it's 2 electrons. Right? And so we use both in this class. But if it's just the fish hook or the barb, where there's only one kind of part coming off, it's 1 electron. Sorry, and I put 2 E's and I really meant to minus. If it's a double-headed arrow, it's 2 electrons. Right? And so those electrons will move over. And what we're trying to get to is if you look at the bottom, here's our valence electron. So it's the 3s1 and it has 1 electron. Fluorine's valence electrons has 2 plus 5 is 7. And so what we're going to do is actually take this 1 electron and push it into that phosphorus. Right? And if we push it into that phosphorus, or sorry, not phosphorus, the p orbital. I'm sorry about that. The p orbital will push the 1 electron in. It's going to give you 6. And now we have a total of 8 electrons. And over here, we actually lose this 3s. And what we actually get is a filled valence shell of the previous one. Right? And so this is going to help us keep those valence electrons where it's a complete octet. Right? So it's trying to look like a noble gas. And whether it's filling the orbital that it has, or if it actually has to go back a shell, that's fine too. We just want to have a completely filled outer shell. So that was ionic bonds. When we have covalent bonds, we're actually going to share electrons. Right? So what we're going to try and do here is we're going to try and put the two electrons together. Right? So what we're going to do is each of these hydrogens has one valence electron, and we're going to stick them together. So these two hydrogens are going to come together. This hydrogen is going to come together, and we're going to make a bond. Okay? So we'll bring the two hydrogens together, and they each are sharing, so the electrons are coming together, and we make a bond. And so one thing you might want to add is one line equals two dots. And so same thing here, two electrons, two electrons. Now, so we typically see this when the electronegativity difference is smaller than that for the covalent bonds, right? So if the covalent bonds is 1.9 or greater, then we completely transfer the electrons. If it's less than that, we're going to share them, right? And we don't always share them equally. So if one atom is much more electronegative, the electrons are going to sit closer to that atom, but regardless, they're going to share. Now, one of the things we'll work on as we go forward is depending on the number of lines between two atoms, we can share different amount of electrons. So for example, if we have carbon dioxide, so CO2, we're still going to want to get to this magic number of 8. So 8 electrons is going to be our octet rule, right? And that comes from that outer shell. Remember, so the octet rule just means we want to fill up that outer shell. So each of these atoms is going to want 8 electrons, right? If they're sharing, both atoms get to count those electrons, right? So remember, each line counts for 2 electrons. So if we're looking at carbon, it's going to be 2, 4, 6, 8. So my carbon has 8 electrons. If we look at the oxygen, 2, 4, and then we can count each dot. So 5, 6, 7, 8. So it has 8 electrons. And the same thing over here, 2, 4, 6, or sorry, 2, 4, and then we count each one of these, 5, 6, 7, 8. So each atom has its 8 electrons, so we've hit our octet. The one exception that we'll use a ton in this class is hydrogen is good with just 2 electrons. And remember, the reason that is the hydrogen only has the one s. And since it only has that one s orbital, the total number of electrons it can take is 2. So that's why hydrogen will be fine with 2 electrons. One more thing, and this will kind of tie this sharing of electrons together. So we said if you're 1.9 or greater, you're going to make an ion. So if we look here on the bottom, we're an ion, and that means the complete transfer of electrons, meaning one of them is going to get a positive charge and one of them is going to get a negative charge. All right. So if you make an ion, it's going to be that one's going to completely give up an electron and one's going to grab an electron. A good rule of thumb, if you don't have that electronegativity chart with you, is if it's a metal and a non-metal, it almost always makes an ion. Right? So a metal and a non-metal almost always make an ion. All right, the one that's a little bit trickier is if the electronegativity value is less than 0.5. And so where we're getting this is if you just had the value of 2 atoms, you could subtract their value. So if you scroll back up, remember we had that periodic table and it had the electronegativity values of each of them. So if we had the value of each one and we subtract them, that can tell us what that number is. And so when we subtract the two, if that's the difference, falls in either one of these ranges, this is the type of bond. Right? So if it's less than 0.5, we're going to say it's non-polar covalent. Okay? So covalent always means sharing. And what we'll generally say is that if they're non-polar covalent, they're going to share pretty evenly. If they're polar covalent, it means one atom has more of the electron density. All right, so if you're a polar covalent, one of the atom has more of the electron density. And one thing you might want to add to your notes, because we'll use this here in a second, is associate negative charges with electrons. And we've kind of been hinting at that I put this E with a negative charge. So we want to associate negative charges with electrons. So if you're stealing a lot of electron density, or we're pulling the electrons towards us, we're going to tend to have a little bit of a negative charge, right? And so not a formal negative charge like the ions, but we're going to build up that electron density. Right. And that's exactly what this slide is talking about. Right. So as we look at this polar and non-polar covalent bonds, if we take, for example, HCl, we would have gone to that chart and looked up the number. So for hydrogen, it's 2.1. For chlorine, it's 3. All right, so I won't expect you to memorize these numbers. If you need them, I'll give you the chart, or you'll have it available to you. So we would pull those electronegativity values off the chart, and we just subtract it. In this case, the difference is 0.9, which means it falls in that polar covalent. What that is actually telling us is that the electrons, right, so if we scroll down here, remember that line actually means there's 2 electrons. And so it's, where are these electrons sitting? Okay. Are they sitting closer to the hydrogen, or are they sitting closer to the chlorine? And what the electronegativity tells us is that they're actually going to be sitting closer to the chlorine. Right? And if we associate a negative charge with electrons, that means as they sit closer to that atom, it gets a negative charge. So what we're going to do is we can show polarity with these 2 symbols. If you're losing electrons, you're going to get a slightly partial positive charge. If you're gaining electrons, you get a partial negative. And so what this is just telling me is we don't have a formal positive charge, but we do have some positive charge. All right, same thing with this one. We have a partial negative charge. We're building up that negative charge. Not the same as an ion, but there is some negative charge to that atom. And so the way we show that on an atom is we write this for negative, and this one for positive. The other thing we can do is we can show that direction of electrons. And so we're always going to draw this arrow towards the more electronegative atom. All right. And the same thing with the negative charge. That negative charge is always going to be on the more electronegative atom. Right? And so we just want to associate that negative charge with electronegativity, because we're stealing electrons, and electrons have this negative charge to them. So they're going to pull towards that more electronegative atom.